Alright, so we're going to do some examples, but before we do that, repetition is good for learning, so let us repeat the mean value theorem before we get started, just to see if we remember what it is. The mean value theorem says that let f be continuous on the closed interval from a to b, and differentiable where? For what values of a, b? On the open interval from a to b. Then there is a c. Where is the c? In the open interval from a to b, such that, now what's the conclusion of the mean value theorem? The conclusion is that the initial or instantaneous velocity at some point in between is equal to the average velocity. Instantaneous velocity equals average velocity. Therefore it's f prime of c equals f of b minus f of a divided by b minus a. Geometrically, what we're saying is that if we're, oh, let me move those points around so that they're different than last time. The slope of the secant line between these 2 points is the average velocity. And if you have your function coming in here, then this is saying that the tangent line has the same slope. So at some point in between, the tangent line is parallel to the secant line. So geometrically then, tangent line is parallel to secant line. Alright, and so that again is the mean value theorem. Let's try a couple of examples. Example: suppose that f of 0 equals 3 and f prime of x is less than or equal to 5 for all x. How big, or how large, can f of 2 be? By the way, since the derivative is defined for all x, we can assume that the function is differentiable and continuous so that we can use the mean value theorem. Okay, so by the way, you could just reason this out, but it's good to, because we have the mean value theorem sitting here, we want to use that if we can. Let's see, how am I going to use that? Well, how large can f of 2 be? Well, using the mean value theorem, right, you could just set it up, right? The interval is from 0 to 2, and so therefore we have f of 2 minus f of 0 divided by 2 minus 0 is equal to f prime of c for some c in the interval from 0 to 2, but we know if the derivative is less than or equal to 5 everywhere. Good, and so do you see that you can solve this inequality then for f of 2, because that's the only unknown here. F of 2 minus f of 0 is 3 divided by 2 less than or equal to 5, right? 10 plus the f of 2 equals 13, less than or equal to 13. Good, so there 13 is as big as it can possibly be. Good. Now when I said that you could reason it out, here's a way you could reason it out. I'm just showing you this because we didn't have to use the mean value theorem, but I guess we needed to. You need to use the mean value theorem to prove your statement. But if you were just to guess, right, 1, 2, if you're going 2 units over, right, and your derivative is less than or equal to 5, then you know you're going up. And so the question is how big can f of 2 be? Well, what happens, you can find your maximum by maximizing the velocity, right, from our racetrack principle. So what happens if we just take f prime to be equal to 5 for the entire time? Right? If we do that, then this is actually traveling on a line with slope 5, right? And so if you go over 2 units and you have a slope of 5, how far up do you go? You would go 10 units, right? 2 units over with a slope of 5, so m equals 5 in this case. Or you could think of it this way, if your velocity, if you're going at 5 miles an hour and you're driving for 2 hours, you go 10 miles, right? But then, of course, you have to remember that you didn't start at 0, you started at 3 in this case. Right, so therefore, altogether then, f of 2 must be less than or equal to 13. Good. Okay, so that's kind of the underlying reasoning as well. All right, let's try another example. True or false? If f prime of x equals 0 for all x, then f of x is constant. Sure, that's true. Alright, because what does it mean for f of x to be constant? If we wanted to use the mean value theorem, we could take f of x to be any number. Well, let's just say let x1 be different than x2. Right, then just using mean value theorem, you could say f of x1 minus, I got something going on here, one sec. Okay, so if I look at the difference between f of x1 and f of x2, I could just go ahead and write this as a quotient using the mean value theorem. And so if I look at the difference, then I've got f prime of c equals 0 for some c between x1 and x2. And so therefore, what happens, whoops, geez, I keep hitting the wrong thing here. F of x1 minus f of x2 must be equal to 0. And so therefore, f of x1 must be equal to f of x2. And if the y values are all the same, that must mean that your function is a constant. Good. Alright, and so that's proving that the statement is true. Alright. Now, something that's a little bit different is it true? If you have two functions whose derivatives are the same, are the functions necessarily the same? So if f prime of x is equal to g prime of x for all x, in fact, in this case, let's go ahead and just say for all x in an interval from a to b, what can we say about f prime versus g prime? Well, let's just go ahead and say, is f of x equal to g of x? Well, from this previous statement here, we see that so kind of the reasoning is that if f prime equals g prime for all x in AB, then f prime of x minus g prime of x equals 0 for all x in AB. And by our previous line here, we know that that function then must be a constant. So therefore, f prime, f of x, the antiderivative, the original function must be a constant, right? Good. So therefore, what we see here is that f of x must be equal to g of x plus c for some constant on the interval from a to b. And so kind of the summary here is that if you have two functions whose derivatives are the same, then the original functions can differ by at most a constant on the interval from a to b. Good, and so that'll come into play later on, but theoretically I think it does make sense, right? Because if you just differentiate both sides of this equation, you get that f prime equals g, right? G prime. Okay, let's see. One last question we'll try. Does there exist a function for which f of 0 equals minus 1, f of 2 is equal to 4, and f prime of x is less than or equal to 2 for all x? Well, let's see. What's going on here? It's always good to draw a quick sketch of what you're looking at. F of 0 is minus 1. F of 2 is 4. f prime of x is less than or equal to 2. Where's that coming from? Well, let's see. If I were to kind of max out my velocity here, or my slope, that you could say is at 2, can I get from this point to this point? From this point to this point? That's 1, 2 over, and 1, that's 4, and 1 is 5. So this is height of 5, and this is height of 2. That's not going to happen, right? No. And so one way you could prove this without just drawing a picture is to just look at f of 2 minus f of 0 divided by 2 minus 0, and that is 4 minus 1 divided by 2. That is your 5 halves, right? And 5 halves is bigger than 2, which is equal to f prime of c, right? And so we would have a problem then. Good. Oh, I already said no. Okay. Very good. Okay, so if you're not sure about what to do in a problem like this, it's really good to draw a picture first, just to see what's happening, and then see if you can reason out the process. Good. That's it for the mean value theorem. We'll go through, so this is the ending of 4.2 today.